Hello guys, welcome back to my channel. In this video, I would be showing you how to design a constant current LED driver circuit, a very simple two transistor constant current LED driver circuit. And before this, I would show you how to draw the DC characteristic curve of the LED, that is voltage, forward voltage versus the forward current of the LED. So let's begin. uh, Create new schematics. Okay, so first of all we have to find LED a favorite type of LED, and I would select a very popular OSRAM LED. OSRAM LEDs are very famous in the sense that they have a wide range of LEDs available. So this is their web page, and we would go find the LEDs here, because this company also provides the spice models of the LEDs. So I would use their spice models as well. Products and light emitting diodes. Infrared emitters. Let's check infrared emitters. Infrared LED is also a type of LED. IR emitters. Let's check IR emitters. And there are various types of LEDs, right? So which LED to select? We would select a through hole LED first of all, and let its current be 100 milliampere current. SFH4851 seems better to me. Tools. Optical simulation. They provide the optical simulations as well. So let us first see what spice models they have, and we would select only that LED whose spice model is available in this OSRAM website. So let us see the spice model, where we would see electrical simulations, IR components, infrared emitters, pspice libraries. Okay, so here you can see that there are various types of libraries, pspice libraries available. We can import this third party spice model into our LTSpice schematics. I will show you how to do that. So let's begin with this first OSRAM IR 5mm radial type of LED. Okay, I will now open that downloads. So guys, this is the LED which we have selected. So this is the series of LEDs, and it has various part numbers. So let us select SFH4550. maybe you can select any of them. Let us select this one. Click copy, and in our schematic here is the spice directive, and paste, control V paste, and that's it. We have placed the model of the spice model of the IR LED. So now let us place diode here, and here the name of the diode would be exactly as it is in the spice model, this name. So control plus right click, double click on the value, control V paste, okay. Now the diode has been named correctly. Now we would place the DC battery source in miscellaneous battery. Now we put place a resistor. Place a resistor like this, because this is a series circuit, so we can place a resistor in series with the LED. Place ground connection. Connect ground. Now let this resistor be equal to 1 ohms, let's say, and this to be equal to 12 volt DC 12 volt battery. Now we would now do the DC sweep analysis. DC sweep analysis, and the voltage source name is V1. Okay, sweep type would be linear, and let's say we are going to sweep this SFH4550. SFH4550. Here search SFH4550. This is the LED. Now let's see what the data sheet says about the SFH4550. We would compare this data sheet curve with our simulation curve. We would compare that. This is the forward current versus the forward voltage drop of the LED. Our simulation curve should come to be like this on the left side. You can see my cursor, this curve. So the DC sweep would be from 0 volt to 3 volt with a step of 0.5 volt. So we would set start voltage 0 volt, stop voltage 3 volt, and step of 0.5 volt. Place anywhere on the schematic, and the current should be peaking up to 1 ampere. 10 raised to the power 0 equals to 1 ampere. So the current should start nowhere from 10 raised to the power minus 4 ampere to 10 raised to the power 0 ampere on semi-log plot. Okay, we would see what comes up in our simulation. Now I think everything is set. Yes, let's perform sweep analysis, DC sweep. Now move the pointer on this current diode. This would show the diode current as we require here. This is the curve that we obtained. This is not exactly the same as the curve in the data sheet, right? So we have to do some tweaks. The tweak here would be to adjust this y-axis to the logarithmic scale, and as you can see, the 10 raised to the power minus 4, we have 10 power minus 4, so the 10 power here is minus 17. We would set it to minus 4, and upper limit is okay. See, now the curve is really resembling this our curve, but we can increase the step size to somewhat more finer sweep, 0.01 volt increment, so the curve would be more nicer in this way. Now again set this to minus 4. Okay, now as you can see, the curve perfectly resembles with the curve in the in the data sheet, and we can also adjust the x-axis also. This is 300 millivolt. We need 500 millivolt, means 0.5 volt. 0 volt to 3 volt with the step of 0.5 volt here. So now the curve is exactly the same as the curve of the IR LED in the data sheet. Right, now we move on to the constant current LED circuit. For the constant current LED circuit, we need to use a two transistor. The one of the both transistors would be NPN BJT transistors. One NPN BJT transistor would be used to drive the collector current to the LEDs, while the other transistor would shunt the base current of the first transistor in order to keep the constant current at the load LED even when the voltage at the input increases. We would see here, let's select BC547 and let's place a transistor first of all, NPN, and pick new transistor, sort the parts with part number wise, come into BC547. This is BC547, right? BD139, the other transistor we would take as BD139, but BD139 would be, of course, is not in the library of the LTSpice, so we have to download the model of BD139. Again, we would select ON-SEMI. ON-SEMI is also a very famous supplier, manufacturer, which supplies the spice model, pspice models of various semiconductor devices. So we will write it here simply BD139, press enter. So here is the transistor comes. Now BD139 is a 1.5 ampere transistor, so this is really a big transistor which can easily shunt the current of the main transistor BC547. So now let's see if they have the spice model. Yes, they have spice model, saber model, pspice model. We would download the pspice model. Here we have got the pspice model of the BD139. Now let's open that. Here you can see this is the model of the BD139 we got. Simply Control C and come on to the schematics and place this model, Control V here, right? So LTSpice, in LTSpice you can place the model anywhere on the schematic and simply use this name again, as I have already mentioned that we have to use this name exactly in our symbol. Copy and Control plus right click, double click on value, Control V, paste. That's it. Now this transistor would use this model while simulation. Okay, now we are going to design our circuit, a very basic circuit. This hand is used to move the component without disturbing the wires. You simply pick the component anywhere, just left click on this, and you can place it here. While and F9 is used to undo. It is not going to. Okay, so and this drag which moves the wire along with the component. So this is something I wanted to mention. Now delete this wires, connect them together. Control plus E is used to mirror the component. let's say it's 2.2 kilo ohm. Okay, now obviously this transistor would this transistor Q2 would shunt the base current of this transistor Q1 as soon as this resistor um, maintains the biasing voltage of this transistor. So as a reference we select this resistor to be equal to 5 ohm. Okay, now as the collector current flows through this transistor into this current sense resistor, this is actually the current sense resistor. So as soon as the current flows through this current sense resistor, the voltage appears across this base of the Q2. Hence this Q2 would get switch on and shunts the current of this base to the ground, right? But if the current is not enough in this resistor, the biasing voltage at the base would not appear and this transistor would not conduct, and hence this transistor base current would not be shunted and this transistor stays in conduction and stays on. So the current would flow through this and increases as the voltage is increased. So now let's again simulate and do DC sweep V1. Now let us sweep the voltage from 5 volt. Let's say our power supply is not very stable, it can fluctuate between 5 volt and 12 volt. So 12 volt and okay, 0.01 volt increment step, correct? Okay, now we can move this model some bit closer and move this to over here. Now this is more clearer view. You can zoom to fit simply like this. Now let us see what happens when we sweep this source DC sweep and see the diode current. See, as you can see now that the voltage is increasing from 5 volt up to the 12 volt range, but the current is not increasing very much significantly, although the current is 62 milliampere at 5 volt supply, while the current only increases to about 6 milliampere up to 68 milliampere at 12 volt. So you can say that the current through the LED is constant at a wide range of supply voltage, right? We can make it more clearer by making this top maximum limit to 70 milliampere and let's set this to 5 milliampere step, and the bottom is 60 milliampere. Now let's see, 60 milliampere, 65 milliampere, 70 milliampere. As you can see, the current is between 60 milliampere and 70 milliampere, but for the voltage of 5 volt to 12 volt, right? Also, we can perform the DC operating point analysis as well. You can simply place this DC operating point analysis here, and you just notice that when I place this DC operating point analysis, this DC sweep analysis already got commented. This is now, this semicolon indicates that this simulation would not be performed as I hit the simulate button, but this simulation would perform. Now I hit the simulation button here. These are the voltages and currents, node voltages and current through the components, summary of it. This is very helpful in getting the analysis of the circuit. As you can see, the current through the diode is 67 milliampere. Alright, 0.067 ampere means 67 milliampere, 67.6 milliampere. We can see this in transient analysis. Let's see, transient 100 millisecond, let's say. Okay, now this has also been commented, semicolon appeared also here, and now transient will run. I hit the simulation button and transient simulation will run. Current through the LED diode. Now as you can see that the current is 67.6 milliampere as we found in the DC operating point analysis. 67.6 milliampere constant over 0 millisecond to 100 millisecond, right? This is the DC current. What else can be done here? Yes, we can sweep the temperature as well by removing this semicolon and putting the dot over here. Now this operating point analysis would be performed, and we can use a temperature sweep, dot step temp. We want to sweep the temperature from 0 degrees centigrade to 100 degrees centigrade in the step of 10 degrees centigrade. See, now as you can see, the curve has been changed, and the current through the LED drops very much significantly as the temperature increases from 0 degrees centigrade to 100 degrees centigrade. Again, we can move the cursor at the ambient temperature. Ambient temperature is 25 degrees centigrade, and at 25.0 degrees centigrade the current is again the same as we found from the DC analysis and transient analysis, that is 68 milliampere. Alright guys, so as we increase the temperature from 25 degrees centigrade room temperature to, let's say, 50 degrees centigrade, the current has dropped to 58 milliampere, and this is a somewhat bigger drop from 68 to 58 milliampere. And as we go up to the 80 degrees centigrade, the current is also dropped, but this current is not such a small current that it would turn the LED off. This current is more than enough for the LED to operate. So as you can also see that the upper limit is within the maximum absolute maximum rating of the LED current. The absolute maximum rating of the LED current is 100 milliampere, as we can see in the data sheet. Here, absolute maximum rating maximum rating of forward current is 100 milliampere, right? So this is perfectly fine within the tolerable range and not much less, so that the LED could turn off. So this was all about the constant current LED circuit. I hope you learned something about the constant current LED and LED characteristic curve as well. If you like my video, please do like it and share with your friends, and please subscribe to my channel. I am sorry I was not available for the previous 2 days, and I would now try to maintain the contents and upload new contents every day. Thank you very much, guys. See you later. Bye bye.